Good morning to all of you. My name is Divya from BSc Chemistry Honours final year. Today we will read on topic photochemistry, that is from Pradeep publication for visually impaired students. So chapter number 4, photochemistry. Introduction. Interaction of radiation with matter. Photochemistry is defined as that branch of chemistry which deals with the study of interaction of radiation with matter resulting into a physical change or into a chemical reaction called photochemical reaction, whose rates and mechanisms are studied after initiation by the radiant energy. Though the term radiation includes all types of electromagnetic waves from very low frequency microwaves to medium frequency infrared, visible and ultraviolet radiation to high frequency X-rays and gamma rays. The radiation of photochemical importance are those which lie in the visible and ultraviolet region from 8000 to 2000 Armstrong, 800 to 200 nanometer. Thus, the two main processes studied under photochemistry are first photophysical processes, second photochemical processes or photochemical reactions. Photophysical processes are those processes which takes place in the presence of light but do not result into any chemical reaction. These processes arise on account of the absorption of light by the substances followed by the emission of the absorbed light. If the absorbed light is emitted instantaneously, the process is called fluorescence. If the absorbed light is emitted after some time lag, the process is called phosphorescence. Further, if the energy of the light absorbed is sufficiently high, the electrons may not only jump to the outer levels but may leave the atoms completely. The process is called photoelectric effect. Thus, photophysical processes include phenomena like fluorescence, phosphorescence, and photoelectric effect. Photochemical reactions are those reactions which takes place by absorption of light by the reacting substances. These reactions are generally brought about by the absorption of light radiations of the visible and ultraviolet region, which lie between 8000 to 2000 Armstrong as already mentioned above. In these cases, the light energy absorbed is stored within the substance and then used for bringing about the reaction. A large number of different types of reactions can be brought about by exposure to suitable light, that is synthesis, decomposition, oxidation, reduction, polymerization, isomeric change, etc. Two well-known examples of photochemical reactions are given below. First, combination of hydrogen and chlorine to form hydrogen chloride. H2 gas plus Cl2 gas gives 2HCl gas in the presence of light. Second, photosynthesis of carbohydrates in plants taking place in presence of chlorophyll are green coloring matter present in the leaves. 6CO2 plus 6H2O gives 6C6H12O6 plus 6CO2. It may be pointed out that the photochemical reactions takes place when incident photon has sufficient energy so that it can result in the excitation of one of reactants from ground electronic state to excited electronic state. Example, Br2 in a mixture of H2 and Br2, as will be discussed later in this chapter. Article 4.2, difference between photochemical reactions and thermochemical reactions, or simply called thermal reactions. The main points of difference a photochemical reaction and a photochemical reaction are summed up in table 4.1 given below. Table 4.1, difference between photochemical reactions and thermochemical reactions. Thermochemical reactions, photochemical reactions. Thermochemical reactions. In these reactions involve absorption of heat. They can take place even in the dark. Temperature has sufficient effect on the rate of thermochemical reaction. The free energy change delta G of a thermochemical reaction is always negative. In these reactions, activation energy arises from the intermolecular collisions or it is supplied in the form of heat. When a reaction mixture is exposed to heat radiation, all the reactant molecules absorb these radiations and get excited almost to the same extent, that is, there is no selectivity. Photochemical reactions. First, these reactions involve absorption of light. The presence of light is the primary requisite for the reaction to take place. Temperature has very little effect on the rate of photochemical reaction. Instead, the intensity of light has a marked effect on the rate of photochemical reaction. The free energy change delta G of a photochemical reaction may not be negative. A few examples of photochemical reactions for which delta G is positive and still they are spontaneous are A. Synthesis of carbohydrates in plants ozonation of oxygen, decomposition of HCl into H2 and Cl2. In these reactions, activation energy is acquired by absorption of photons of suitable energy. When a reaction mixture is exposed to light radiation, the molecules of one of the reactants may get excited independent of the presence of other species, that is, only Br2 molecules in a mixture of H2 and Br2. In the present chapter, we shall discuss mainly the laws of photochemistry, examples of some photochemical reactions, the mechanism of which they proceed, and certain terms like fluorescence, phosphorescence, and chemiluminescence, etc. Laws governing absorption of light. When a monochromatic light consisting of a single wavelength is passed through a medium, some light is absorbed by the medium and hence the intensity of the incident light decreases. The decrease of intensity on passing through a pure homogeneous medium, that is a pure liquid, is governed by Lambert's law, and the decrease of intensity on passing through a solution is governed by Beer's law. First, Lambert's law. This law, put forward by Lambert in 1760, states as under: when a monochromatic light is passed through a pure homogeneous medium, the decrease in the intensity of light and with the thickness of the absorbing medium at any point x is proportional to the intensity of incident light, that is the intensity of light at the point x, that is just before entering into the thickness dx mathematically. Minus di by dx is proportional to I, or minus di by dx is equals to ki. Equation number 1, where di is the small decrease in intensity of the light on passing through a small thickness dx, I is the intensity of the incident light just because entering the thickness dx, and the constant of proportionality k is the absorption coefficient depending upon the nature of the absorbing medium. The intensity I at any point x at a distance x from the start of the medium can be found in terms of the original intensity I naught as follows. Equation 1 can be written as di by I is equal to minus k dx. When x is equals to 0, I is equals to I naught, x is equals to x, I is equals to I. Integration equation number 2, between the limits x is equals to 0 to x is equals to I is equals to I naught to I, we get I naught से I, integration of di by I is equals to x is equals to 0 to x is equals to x, integration of minus k dx. और ln I by I naught is equal to minus kx, I by I naught is equals to e की power minus kx, और I is equals to I naught e की power minus kx. Equation number 4. This equation expresses how the original intensity I naught is reduced to intensity I after passing through the thickness x of the medium. The difference between I naught and I obviously gives the intensity of absorbed. Thus, I absorbed is equals to I naught minus I is equal to I naught minus I naught e की power k minus kx. Equation 4 can be expressed in another form which can be derived for as follows. Equation 3 can be written as 2.303 log I by I naught is equal to minus kx, or log I by I naught is equals to minus k by 2.303 into x. Log I by I naught is equal to minus k dash into x, or I by I naught is equal to 10 की power minus k dash x. I is equals to I naught into 10 raised to the power minus k dash x, where k dash is equal to k by 2.303 is called extinction coefficient of the substance, that is of the absorbing medium. Now it is this quantity which is called absorption coefficient or absorbability of the substance. The physical significance of the extinction coefficient or absorbability follows more clearly from equation 6, which can be rewritten as k dash is equal to minus 1 upon x log I by I naught is equal to 1 by x log I naught by I. Log I naught by I is equal to 1, k dash is equals to 1 by x. But log I naught by I is equals to 1 means I naught by I is equals to 10, that is I is equals to 1 by 10 of I naught. Hence, extinction coefficient or absorbability may be defined as follows. The extinction coefficient or absorbability is the reciprocal of that layer thickness expressed in centimeter at which the intensity of the light falls to 1/10 of its original value. Second, Beer's law. This is an extension of Lambert's law put forward by Beer in 1852. It is applicable to solutions and states as under. When a monochromatic light is passed through a solution, the decrease in the intensity of light with the thickness of the solution is directly proportional not only the intensity of the incident light but also the concentration C of the solution. Thus, for a solution mathematically we have minus di by dx proportional to I into C minus di by dx is equals to epsilon ic. Epsilon is pronounced as epsilon. Equation number 8, where epsilon is a constant of proportionality and it is called molar absorption coefficient. Its value depends upon the nature of the absorbing solute and the wavelength of the light used. Equation 8 can be rewritten as di by I is equals to minus epsilon c dx. As before, integrating this equation between the limits x is equals to 0 to x is equals to I is equals to I naught to I, we get integration of di by I is equals to integration of minus epsilon c is equals to ln I by I naught is equals to minus epsilon cx. Equation number 9. I by I naught is equals to e की power minus epsilon cx. I is equals to I naught e की power minus epsilon cx. Equation number 11. This equation shows that the intensity of monochromatic light decreases exponentially from I naught to I with increase in thickness x and concentration c. The intensity of the light absorbed by the solution when it passes through a light x of the solution will be given by I absorbed is equals to I naught minus I is equals to I naught minus I naught e की power minus epsilon cx is equals to I naught into 1 minus e की power minus epsilon cx. Equation number 12. As before, equation 9 can be expressed in another form. For this purpose, we can rewrite equation 9 as 2.303 log I by I naught is equals to minus epsilon cx, or log I by I naught is equals to minus epsilon by 2.303 cx. Log I by I naught is equals to minus epsilon dash cx. I by I naught is equals to 10 की power minus epsilon dash cx, or I is equals to I naught into 10 की power minus epsilon cx. Equation number 14. Where epsilon dash is equals to epsilon by 2.303 was earlier called molar extinction coefficient of the absorbing solution. Now it is this quantity which is called molar absorption coefficient or molar absorbability of the absorbing solution. The physical significance of molar extinction coefficient or molar absorbability follows from equation 13, which can be written as epsilon dash is equals to minus 1 upon cx log I by I naught is equal to 1 by cx log I naught by I. If C is equals to 1 molar and log I naught by I is equals to 1, then epsilon dash is equals to 1 by x. As before, log I naught by I is equal to 1 means I naught by I is equal to 10, that is I is equals to 1 by 10 of I naught. Hence, molar extinction coefficient or molar absorbability may be defined as the reciprocal of that thickness of the solution layer of 1 molar concentration, which reduces the intensity of the light passing through it 1/10 of its original value. It may be pointed out that gases follow Beer's law, not Lambert's law. Units of molar absorbability or molar absorption coefficient from equation 13. Epsilon dash is equals to minus 1 upon cx log I by I naught. Log I by I naught is a dimensionless quantity. The SI units x is in meters, m and c is in mole per meter cube. Hence we have epsilon dash is equals to meter cube mole inverse. Meter inverse is equal to meter square mole inverse. However, usually concentrations are expressed in mole per liter, molarity m, and length x in centimeter. The units of epsilon dash will then be epsilon dash is equals to liter mole inverse centimeter inverse is equals to meter inverse molar inverse centimeter inverse. Some other terms commonly used in spectrophotometry. Spectrophotometry deals with the measurement of intensity of the light absorbed when it is passed through a sample of known thickness and concentration, that is measuring the intensity of transmitted light IT relative to that the incident light I naught. It is especially useful when one substance or that only one in the reaction mixture has a strong absorption in the spectral range. In these studies, the following terms are commonly used. First, transmittance. The ratio I by I naught, that is the ratio of intensity of the transmitted light from the solution of the intensity of the incident light I naught, that is the fraction of the incident light transmitted, is called transmittance T. Transmittance is equals to I by I naught. Second, absorption or optical density or extinction. The logarithm of the reciprocal of transmittance log I 1 by T or log I naught by I is called absorption A or extinction E, formerly called optically active density T. Absorption A is equals to extinction E is equals to optical density D is equals to log 1 by T is equals to log I naught by I. Equation number 16. Third, specific extinction coefficient Ks. It is defined as the extinction or optical density of absorbance per unit length and unit concentration of the solution. Ks is equals to D by Cx. Fourth, molar extinction coefficient. Substituting the value from equation 16 in equation 13, we get I by I naught minus is equals to minus log t is equals to a or d is equals to epsilon dash cx, equation number 70. Thus, if x is equals to 1 centimeter and c is equals to 1 mole per liter, epsilon is equals to d or a, hence molar extension coefficient may be defined on the optical density or absorption of solution having 1 centimeter thickness and concentration equal to 1 mole per liter. Further, from equation 17, minus log I by I naught is equals to minus log t or a or d epsilon dash cx. Thus, a plot of absorption A versus concentration C will be a straight line passing through the origin with a slope epsilon dash x as shown in figure 4.2. Figure 4.2, plot of absorption versus concentration C of the solution. The dotted portion of the curve shows deviation from linearity at higher concentration. Limitations of Beer's law. First, the law holds good only for monochromatic radiation. Second, the law is applicable only to dilute solutions at higher concentration. The interionic interactions disturb the absorption of incident radiation as shown in figure 4.2. Third, the temperature should almost remain constant. Too much rise in temperature shifts the absorption band towards longer wavelength called bathochromic effect. Numerical problems on Lambert's law and Beer's law. Formula and units. First, for light passing through a pure homogeneous medium, Lambert's law, ln I by I naught is equals to minus kx or log I by I naught is equals to minus k by 2.303x is equals to minus k dash x, where I naught is the intensity of the incident light, I is the intensity after passing through a distance x in the centimeter medium, k dash is the called the absorption coefficient or extension coefficient. If x is the total length of the medium, I is equals to I t is the intensity of the transmitted light. Second, for light passing through a solution, Beer's law, ln I by I naught is equals to minus epsilon cx or log I by I naught is equals to minus epsilon 2 by 2.303 cx is equals to minus epsilon dash cx. When I naught and x have the same meaning as explained above. C is the concentration in moles per liter. Epsilon dash is called molar absorption coefficient or molar extension coefficient. Third, I absorbed is equals to I naught minus IT. Fourth, minus log I by I naught is equals to minus log T is equals to A or D minus epsilon Cx, where I by I naught is equals to T is transmittance, A is called absorption and D is optical density. Example 1. When an incident of wavelength 3000 Armstrong was allowed to pass through 2 mm thick Pyrex glass, the intensity of the radiation was reduced to 1/10 of its initial value. What part of the same radiation will be absorbed by 1 mm thick glass? Solution. In the first case, we are given that IT by I naught is equals to 1 by 10, x is equals to 2 mm is equals to 0.2 centimeter. Applying Lambert's law, we have log IT by I naught is equals to minus k dash x. Log 1 by 10 is equals to minus k dash into 0.2 or k dash is equals to 1 by 0.2, that is 5. In the second case, we are given x is equals to 1 millimeter to 0.1 centimeter. Using k dash is equals to 5 as calculated above and applying Lambert's law, we have log IT by I naught is equals to minus k dash x is equals to minus 5 into 0.1 is equals to minus 0.5. IT by I naught is equals to anti log minus of 0.5 is equals to anti log 1.5 का bar is equals to 0.3162. IT is equals to 0.3162 I naught. I absorbed is equal to I naught minus IT is equals to I naught minus 0.3162 I naught is equals to 0.6868 I naught. 68.38% of the intensity of incident light. Example 2. Calculate the transmitted absorptions and absorption coefficient of a solution which absorbs 90% of a certain wavelength of light beam passed through 1 centimeter cell containing 0.25 solution. Solution. We are given that I absorbed is equals to 0.20 I naught, x is equals to 1 centimeter, c is equals to 0.25 molar. IT is equals to I naught minus I absorbed is equals to I naught minus 0.90 I naught is equals to 0.10 I naught. Transmittance. T is equals to IT by I naught is equals to 0.10. Absorbance. A is equals to minus log IT by I naught is equals to log I naught by IT is equal to log 1 by 0.1 is equals to 1. Applying Beer's law, we have log IT by I naught is equals to minus epsilon dash cx. Log 0.10 is equals to minus epsilon into 0.25 into 1. Minus 1 is equals to minus epsilon into 0.25. Epsilon is equals to 4.0 liter mole inverse centimeter inverse. Alternatively, A is equals to epsilon dash cx. Epsilon dash is equals to A by cx is equal to 1 by 0.25 into 1 is equal to 4.0 liter mole inverse centimeter inverse. Problems for practice. First, if 2 millimeter thick plate of a material transmits 70% of the incident light, what percentage will be transmitted by 0.5 millimeter thick plate? Answer: 91.47%. A certain substance in a cell of length L absorbs 10% of the incident light. What fraction of the incident light will be absorbed in a cell which is 5 times? So this is completed the chapter. Thank you so much.